All right, let's wrap up section 4.2. I'm Gregory Carlson. Let's look at a few application problems of exponential growth. And one of them is compound interest, which is an incredibly exciting topic and what Einstein called the most powerful force in the universe. And so say you took some money, put it into a bank or into a stock or something that is growing at some rate. How would you calculate how much money you have? So this is a very important formula and you should memorize it. And that formula is the future value of your money. So you put some money into a bank account. The future value of your money, which is A, is based on the amount of money you started with, which is your principal. So the future amount of money is equal to your principal times a multiplier. And the way we calculate the multiplier is as follows. 1 plus, okay, and then you do your interest rate divided by the number of times you compound a year, okay? Then you take that to a power of the number of times you compound a year times the number of years, t. And that's the formula. So the future value of your money that you put into a savings account is based on the amount of money you started with, your principal, times this multiplier. And the way you come up with the multiplier is 1 plus the interest rate divided by the number of times you compound, raised to the number of times you compound times the number of years. And by the way, t is usually almost always in terms of years, and n is usually in terms of number of times per year. So if you compound twice a year, or semi-annually, that would be 2. Or if you compound quarterly, n would be 4. Or if you compound monthly, n would be 12, and so on. So let's look at an example and see how these numbers come together. We want to have 6,000 in our retirement account in 8 years. If it is compounded quarterly at 7.5%, how much principal should we start with? What should the present value of the account be? So, in other words, this question, they tell us it's kind of like retirement planning. We want to have $6,000 in this retirement account. So we'll plug in that value for A. We don't know how much we need to start with. And so that's why we're going to call that P, because we don't know what that number is. Let's plug in the rest of the numbers. It's always 1 plus. Now, our interest rate should always be a decimal. And so you see that we have 7.5%. So that's 0.075, because 7.5% as a decimal is 0.075. That's divided by the number of times we compound per year. And we see that we're doing it quarterly, so that means a 4. What goes up here? We have n times t. We're compounding quarterly, so that's a 4. For 8 years, so that's an 8. So there you go. It's 6,000 equals p parenthesis 1 plus 0.075 divided by 4, all to the 4 times 8 power. It looks pretty bad, but as long as we have a calculator, we can calculate it pretty quickly. So let's see if we can simplify this. First, I notice that we have 4 times 8. That's the same as 32. So let's put that in the back of our head. I will always start on the inside and work out. So 0.075 divided by 4 equals, again, notice I never try to put too much in the calculator all at once. Now we are going to add the 1. So plus 1. So this number is the inside of the parentheses, 1.01875. So now let's take that to the 32, which remember is 4 times 8. So I'll hit my exponent button to the 32 power, and I get that, which is my multiplier. So 6,000 is equal to P times, I'm going to do a lot of decimals, 812023793. So all of those numbers crunched down to 6,000 equals P times this number. So to solve, just divide both sides by this 1.812023793 number. That will tell us how much we need to start with. So I'm going to clear that. 6,000 divided by 1.8 1,202,3793. So the amount of money we need to save right now, and I'm going to round to the penny. So if we want to have $6,000 in this retirement account, we need to save $3,311.21 right now. If we compound it once a quarter at 7.5% for 8 years, our money will essentially double, going from $3,311, a little less than doubling, going up to $6,000. So hopefully that process makes sense. Let's go ahead and do the next one. In fact, maybe, well, let's take a look at it. Find the required annual interest rate to the nearest tenth of a percent for 1,100 to grow to 1,800 if interest is compounded monthly for 9 years. So again, let's write down our formula. Again, you should try to memorize this. There's the compound interest formula. A equals P times 1 plus R over N to the NT. So let's plug in what we know. We want 1,100 to grow to 1,800. So that means our final value is 1,800, and our initial value is 1,100. Does that make sense? Our principal is 1,100, and it's going to grow to 1,800. We need to know the interest rate. It says find the required annual interest rate. So I don't know what that is, so I'm going to call it R. We're compounding monthly. So that means N is equal to 12. Also, N is equal to 12 up here, and we're doing this for 9 years. So there you go. That's going to be the formula we get. So we need to solve this equation for R. The first thing we should do is make this 1,100 go over here. The 1,100 is dividing, the 1,100 is multiplying, so we divide to cancel it. So let's do 1,800 divided by 1,100. Which is, I'm going to write it over here, 1.63636, I'll round it to 4. And that's going to equal 1 plus R over 12 to the 12 times 9, I believe, is 108. And so that's to the 108th power. All right, so we have 1.636364 equals 1 plus R over 12 to the 108th power. So here's what you have to do now. In order to get this exponent to go away, we need to do the opposite of this exponent, which means taking a root. To get rid of this, if this was a 2, we would take the square root of both sides. Since it's a 108th, we take the 108th root of both sides. And I know that sounds kind of crazy, but we take the 108th root of both sides. And basically what that does is it cancels the exponent. So on the right, we just get 1 plus R over 12, which is nice. So now we need to take the 108th root, not 180th root, the 108th root of the left. So here's how you do that on your calculator. First, you type in 108, because that's the root we're taking. Then you hit the button on your calculator that's x root of y. So hit that cat button, because that plugs in the x. And now we plug in the number we want, 1.63, oops, I messed it up, so start over. First plug in the root you want to take, then hit x root of y. Now plug in the number inside, which is 1.63, oh, I did it again. 108, boop, 1.636364. That's not right. I think I did it backwards. Every calculator is a little bit different. I think on this calculator you might need to type in this number first. And again, every calculator is a little different, so you should get to know your calculator. That's correct. It should be a number that's just over 1. So there we go. So notice that it's a number just over 1, and you know you're on the right track. That's how I knew 17 was crazy. There's no way it was 17. It should be a number that's slightly bigger than 1. So on my calculator, I have to type in the inside number first, then the outside. Other calculators are the reverse. Let's finish solving this. Subtract 1 on both sides. We get 0.00457038 equals r over 12. And it looks like we're going to get a decimal, and that's good because our interest rate will be a decimal. So finally, just multiply both sides by 12, and we're done. Okay, so take that number minus 1, and then we times it by 12. And we get our final answer. R is equal to 0.054844, and then round the next number to a 6. So there's our interest rate, and remember to turn a decimal into a percent, multiply by 100, which moves the decimal to the right 2 places. So we get 5.484%. The problem asked us to round to the 10th of a percent, so the final answer would be 5.5%. Kind of tricky. The trickiest part, I think, was doing the 108th root and figuring out how to do that on your calculator. Let's do this last example, and then this section will be done. There's a very, very, very magic number called e. And basically, e is formed by doing infinite compounding. And e is such a special number that it deserves its own series of videos. So we're not going to get too much into e right now. Just know that e is the result of taking a limit and basically doing an infinite of compounding on a smaller and smaller and smaller, just taking an infinite amount of compounding. And the result is a very special number, usually on most calculators. Here I think it's this button, e to the x. So if I do e to the 1, e to the 1 equals the number right there, 2.718. It's a decimal that goes on forever. It's a transcendental number. It's an amazing number, 2.718. We'll talk about it hopefully in future videos. For now, let's just, the inverse of e is the natural log, which we'll talk about in the next video. Let's see if we can solve this. It's going to be pretty basic. It's basically the same as we did in our last videos and our last problems. E to the 12x minus 1 equals e to the 5x. Again, don't get thrown off by e. It's just a number approximately equal to 2.718. So what do you notice? The bases are the same. So I can rewrite this as e to the 12x minus 1 and e to the 5x. Now, I can do that because remember, when we have a power to a power, you multiply the powers. So that's e to the 5x. Bases are the same, so therefore the exponents have to be the same. 12x minus 1 equals 5x. Now you just solve this. Let's subtract 12x on both sides. Okay, negative 1 on the left is all that remains. 5 minus 12. 5x minus 12x is negative 7x. And then finally just divide by negative 7. So x equals negative 1 over negative 7, and 2 negatives make a positive. So there's the answer to that one. So don't get thrown off by the e. It's a very special number that you should look into, and we'll look at it more in future videos. I hope you enjoyed exponential functions and how to solve them, and I will see you in section 4.3, where we'll talk about logarithms. If this video was helpful, please remember to like and subscribe. If you have any questions, please leave them in the comments. Thanks so much, and see you in 4.3.